Hello there, and welcome back. We're going to continue our discussion about finding volume between surfaces. In the last example, you might remember, we found the volume between a paraboloid and a plane. And we had to find the projection, or the base, that the intersection created with the xy plane. And from there, we were able to find our volume equation. Very lengthy process. The setup's easy, but the process getting there is pretty complicated. So in this example, we're going to take a look at finding the volume of the solid bounded above by the paraboloid. And it's not just any paraboloid, it's our hyperbolic paraboloid. From above and below by the plane z equals -3. So that's going to become a little bit different for us. Given the rectangular bounds 0, 0, 0, 3, 4, 0, and 4, 3. So they're giving us these bounds on the xy plane. So this is going to be our base, and then remember the base is always on the xy plane for us right now. Later on we'll move it to different planes. It's kind of fun. You had a homework like that, you will have a question like that tomorrow night's homework, but for now we're just going to continue everything on the xy plane. So what we're going to do is we're going to draw this. We're going to draw our hyperbolic paraboloid. So if I were to draw this, here we go. Let's sketch this bad boy. Alright, wish me luck. So we have the XYZ plane, and above is by our hyperbolic paraboloid. It's going to open up on the YZ plane, like so, and it's going to touch at 0, 0, 0. So there's our hyperbolic paraboloid, right? And it opens up downwards, like so. Let's see, that's so tough to draw. There we go. And there's our hyperbolic paraboloid. My best one I've drawn to date, probably. Now, it's surrounded below by the plane z equals -3. So I'm going to go and draw that plane way down here. So it's going to intersect the xy plane. And like that. There we go. Now remember, this does keep going down. So there is our plane z equals -3. Right there. But now we're restricting our domain. So our domain is going to be this rectangle, this small, tiny little rectangle, like so. So if we let this represent our plane, remember what we're going to do is we're going to project this plane up to the surface, and we want to calculate the volume within that projection. Sorry, my drawing's terrible. But anyway, let's go get started. So we're going to start off with the base because, like the song says, it is all about that base. My base is from 0, 0, 0, 3, 0, 4, 4, 0, and 4, 3. So there's our rectangular base. Remember, this is being projected to the surface, to our hyperbolic paraboloid. And that's going to give me my limits. So I'm going to use a vertical rectangle here. So that's going to give me my change in y values. My y values are going to go from 0 to 3. Then my x values are going to go from 0 to 4. And now I want to find the volume. Well, remember, to get the volume, we want to find the volume. So if I want to find the volume here, I'm going to take the top and I'm going to subtract the bottom. So this is to get the volume. Is basically the volume is the part between the curves. So we're going to take the volume of our top function minus the volume of our bottom function. We saw that again up here when we did area. If I want to find the area here, I want to find the area of the top minus the area of the bottom. So the concept hasn't changed. So we can write that out. Well, my top is my hyperbolic paraboloid, which is y squared over 2 minus x squared over 3 minus the bottom is at -3. So that's that would give me my volume. And now we're just going to write our integral, our iterated integral. So we would get y squared over 2 minus x squared over 3 plus 3. Now, it's a double integral, so let's talk about this. Well, we're changing the y's first, so we'll go dy, and the y's are going to be evaluated from 0 to 3, And then we're going to multiply that by dx, the change in the x's. And that's going to go from 0 to 4. Remember, this is volume. Right here, these two right here, that's the area of our base right there. And this is our height. And that would give you the volume between those two surfaces. Very easy to do. So easy, a senior in May can do this. I know. I teach seniors in May, and they can do this. Alright. Now the last thing we're going to talk about today is average value. You might recall average value from last year. We had a formula for it. To calculate the average value last year, we used the following formula. And in a nutshell, what this is really saying is, if I have a function between a and b, and that function's all curvy-licious and all, this area underneath here, this is my area, and this is our function. The average value told us what is the average height of our function. We called it our fave last year. It was the average height of our function. Now to get the average height, well, all we do is we find the area and divide it by the base. So, and we can see that algebraically. If I would think about this more algebraically, what this is really saying again from last year, on the domain from A to B, there is a height, our fave. There is a height to which I can draw a rectangle, and the area of this rectangle would be the exact same area of our function. It's the same way we do grades in school. If I put a 75 in for your grade for the semester, that means all your scores average out to be a 75. It's like you got a 75 on everything. And we can verify how the formula works, very simple, because I can just use a little bit of algebra. I know to get the area of my rectangle, it's going to be base times height. Well, my base is this b minus a, and the height is my average value. And we said that's the area. Well, if I want to find the average value, the height of our rectangle, that's our height right there of our rectangle, I can take my fave, and I'm going to divide both sides by b minus a over b minus a. Well, what is a? Well, that's just the area, which is our integral, a to b, a to b, f of x, dx, over b minus a. So that's how we get average value. In other words, the sum of all the rectangles divided by the base gives us the average height, or the y values, of our function. The same is true for multivariable. To calculate the average value of multiple variables, we're going to use the same idea. But if you notice in this case, we're dividing by a. So here is going to give us the sum of all of our values. Well, this a down here, well, what does that a stand for? Well, that is just the area of the base. In other words, think about volume of a cube. Length times width times height. My height, remember, is my average value. In multivariable, that's f of xy. It's the average value of our z values. Well, I can solve for h by taking my volume and dividing it by my length and width. That's the area of our base. So how do we get volume? Well, that's what we've been talking about. It's the integral of our base area, f of xy, dy dx, all over the area of the base. So very simple to do, very easy to set up. So let's go take a look. We want to find the average value of the function 1/2 xy over the region defined by this rectangle. Well, so what do we say? Well, the average value, it's our favorite, is the volume divided by the base. Just this form, don't memorize the formula, just how do you get it? You can take your volume and you divide it by your base. If I want to find my average height, I take my entire volume divided by the area of the base. I only have three variables, length, width, and height. If I'm looking for my average value, which is my average height of a function, I just divide by the remaining two variables. I take my volume, and I can divide by my remaining two variables. So once again, though, it is, like we said, all about the base. So when we draw our base, it is going to be a rectangle, 0, 0, 4, 0, 4, 3, 0, 3. So remember, this is a part that is projected to the function, f of x, y, to our surface. If I look at a vertical rectangle, you can do horizontal if you like, I know my change in y's are going to be 0 to 3, and my change in x's are going to be 0 to 4. The area of my base, well, this is a rectangle, that's just length times width, so 4 times 3, which is 12. So how do I get my fave? Well, remember, it's volume divided by the base. So my volume is my double integral, which we've been working on, 1/2 xy. I did dy dx, so I did y first because I started vertical. I do y first. My y's go from 0 to 3, my x's from 0 to 4, and I divide that by the area of my base. And that is how we get our average value. You can type that in your calculator, or if you're bored, solve it by hand. You should be able to solve it by hand. That's not a bad one right there. All right, so let's take a look at number 4. Oh, no. We'll do this one in the next video. So go on to the next video and we'll take a look at number 4 real quick. Thanks.